Okay.
Okay.
First of all, I must tell you what is
Yes.
a work. Okay, let me see how many things I am going to tell you. Number one, work. What is work? Number two, its formula. Number three, related everything to work. Number four, work done by constant force. Work done by variable force. Work energy theorem. Number seven, work as area under force versus position graph. Then it is power. Then, okay, energy also, right? These are the things that I have to tackle. Maybe one lecture is not sufficient. Maybe it is to be done in 2 lectures. Okay. Number one, work. When you say that you are doing work, when you say that you are doing work,
Yes.
possibly when you are taking an object from one place to another place, right?
Yes.
It is an object of mass m, and you take this object here and you feel that you are doing work. And possibly, if it is a wall and you are here and you are pushing on the wall and you feel you are working, right?
Yes.
And then if you are raising an object in the up direction, you are saying you are doing work, right? And then if is a cord here and you are pushing the cord over a distance and you feel you are working, right? You are applying force F, you feel that you are working. This is our everyday experience. When we push a wall, or when we drive a cart over a distance, and or when we push up an object upwards, when we take an object from one place to another place, then we say we are doing work. Not exactly. No. Work has a definition of its own. If you are pushing a wall, if you are pushing a wall, you are banging against a wall, you feel that you are doing work, but in physics you are not doing any work. So work is said to be done if you apply force, right?
Yes.
But that force should displace an object. It should displace an object. If it is not displacing an object, then no work is done. And force is vector, and it is also vector. And the work done is force and displacement dot of those 2 vectors. This is the definition for work.
Yes.
If F dot S is something, then work is done. If F dot S is nothing, then no work is done. Maybe there is force, maybe there is displacement also, but F dot S is 0, so no work is done. Because you know F dot S is Fs cos of theta.
Yes.
Right? Why theta is the angle between what and what?
The force and the displacement.
Yes, exactly. Theta is angle between force and displacement. Here you see, look at this. If there is force and there is displacement, but theta is 90 degrees or pi by 2, right? Then what is work done?
Pi by 2, I think, is 0. So
Yeah,
work done is
that's what I say. Then you apply force, and there's displacement also, but theta is 90 between force and displacement, work done is 0.
correct.
You may exert a force and there may even be displacement, but the displacement and force has the angle of 90 degrees, and the work done, there's no work done. You may feel that you are doing a lot of work, but no work is done. Now see again here, if theta is 0, then work done is Fs cos of 0. That is Fs, maximum work is done. Just simply, cos 0 is 1, right?
Yes.
If theta is 180 or pi, then work done is Fs cos of pi. And if you know cos pi is -1, is minus Fs. Cos pi is -1, so it's minus Fs. So if theta is 180, then negative work is being done on the object.
Yes.
So these are the simple things of definition for work. Now see, I will give you the examples. See here. Number 1, there's a person. See, I can't make even the figure. There's a person. He has a stone on his shoulder. Is he doing any work?
No.
No, absolutely no. Yes. Suppose he has a stone on his shoulder and he is moving forward. Is he doing any work?
Yes. Or no.
He is moving in the forward direction with constant velocity.
Velocities.
Is he doing any work? See, I will explain you. If he is holding a stone on his shoulder, he exerts upward normal force, right?
Yes.
The force he exerts in the upward direction and the displacement is forward because he is moving in the forward direction. What's the angle between the two?
90.
Work done is 0.
Yes.
So it is surprising that you may have a stone on your shoulder and you move with the stone in the forward direction. You still are not doing any work.
Yes.
A cricket ball moves on the ground, right?
Right.
The gravitational force is downwards.
Yes.
The cricket ball moves on the ground in this direction with velocity v, suppose.
Yes.
And finally the cricket ball stops. Who is doing work?
Gravity.
Why should the cricket ball stop? Because somebody has done some work, negative work on the cricket ball, and it
Yes.
stops. Who does the work?
Friction.
Yes, because friction is backward.
Yes.
The angle between friction and displacement is 180. The work done is negative, that stops it. And generally what we feel, or what we tend to feel, that gravity stops the object. Gravity stops this cricket ball. We feel that this cricket ball is being attracted to the ground downwards and finally it stops. No, because gravitational force does not do any work. Why? Because this is a 90-degree angle between displacement and gravitational force.
Okay.
So
Yes.
here one tends to feel, one has this feeling in his mind that it is the gravitational which stops the ball. But you have said it rightly, it's the frictional force which stops the ball, because frictional force opposed to the displacement, and theta is 180, and work done is equal to Fs minus. You understand my point?
Yes.
And generally it is said that cats eat more than dogs.
Okay.
Why should they do that? You see, it's a ground, right?
Yes.
And dogs are always moving on the ground. When they move on the ground, they don't need to do any work because they are not fighting against the gravitational force. They are moving on the ground, right? Do they fight against the gravitational force?
No.
What's the work done against the gravitational force?
0.
So cats cats, what they do, they make jumps.
Yes.
And they jump up, it's the gravitation which acts down.
Right.
So their displacement is against gravity. So what is the angle between their jump upwards and gravity downwards? 180. So a lot of negative work is being done.
Yes.
Is that right?
Yes.
So cats, when they make jumps upwards, they fight against the gravity because gravity is down, and cats go up against the gravity, and that's why they work. And dogs don't have to work because they move smoothly on the surface of the ground, and they don't have to fight the gravity. Gravity is downwards; they move forward. The angle between the gravity and displacement is 90. So dogs don't do any work. So generally, it is said here, cats eat more than dogs, and the reason is this: cats make jumps, and the dogs don't make any jump. Right?
Right. Yes.
They move on the smooth. Now, I will give you one more example. Suppose you lift a object upwards,
Okay.
then you seem to be working because you are fighting the gravitational force.
Yes.
And if you are taking something in the forward direction, you don't seem to be doing any work. Or if at all you are doing any work, it's very small.
Right.
See, if you are moving object in this direction, it is easier. If you are moving object in upward direction, that's difficult. Here you are working more. Here you are working slight because of this reason. 90 angle means that no work is done. 180 angle means that a lot of work is being done. Okay, this is one part of the thing. Now the next part. Next part is that work done is F dot S. Can you put this force into components? It's IFX plus JFY plus KFZ. You know that how to put a vector into its components?
Yes.
Any vector can be put into three components: X component, Y component, J component, right? The K component. Dot, what is the components of this S, displacement?
Displacement, would it be ISX?
That is good. ISX was better, but I will write just IX plus JY plus KZ. But yours was better. You would like to write SX, SY, and SZ. That's no bad. That was even better. Anyway, yes. So I dot I is 1. So it is X FX plus what's J dot J? 1?
Y.
Y FY. What's K dot K?
ZFZ.
That's Z of FZ. Right? This is one more definition for work done. Sorry. Oh my God, what I'm doing. Oh my God. Oh my God.
Work is not.
Somebody looks at this, it is bad.
Oh no.
It is scalar. It is the dot product of two vectors is scalar. It is scalar. I mistakenly put an arrowhead here. Anyway, this is work done. One more definition. One more definition.
Okay.
Suppose F is equal to 2I plus 3J plus 4K, and displacement or S, same thing, is equal to 2I plus 3J minus 2K. What is work done? That's F dot or this dot this, right?
Yes.
What is F?
2.
How can you find the dot product now? X,
Which,
Fx. That is
yes.
2 into 2.
Which is 4.
That is 4, good. 3 into?
3, which is 9.
4 into 2?
8.
Minus or plus?
Minus.
Good, that is right. You have to multiply this positive and negative, that's negative. So that is 5 is the answer. Joules. Right? So to find work done, you can use one more formula.
Right.
Okay. Now, one more point. Third, work done is also, if you plot a graph, I don't want to go to the integration part of it, but I will tell you one thing. Suppose you plot a graph between displacement and force. But here in the graph, if we want to plot a graph and we want to do something with the graph, then force and displacement must have the same direction.
Okay.
Right?
Yeah.
And you plot a graph like this, okay? This is the graph.
Okay.
X is this, force is this, X is something else, force is this, and there's a different points, and you plot the graph between position and force, right?
Okay.
Suppose I have F is equal to, okay, 2x. Can you plot a graph between force and X? Answer is yes. X is 0 and force is 0. X is 1, force is equal to 2. X is equal to 2, force is equal to 4. X is equal to 4, force is equal to 8. So these values, 0, 4 is 0. X1, 4 is 2. X2, what is force?
4.
X4, what is force?
8.
And then you plot a graph. X versus force, right?
Yes.
Now, first point is 0, 0.
Right.
Second point is 1, 2. There's 1. Okay, let me 2.
2, 4.
X is 1, force is 2. And 2, 4, it is X equal to 2 is 4. Is 4. The graph is like this, right?
Yes.
This is what we have been doing. Not a big deal, right?
Yes.
Suppose there's a graph between force and displacement. If you find area under this graph, this area. But here finding area is a little difficult. Again, you may have to use the integration. If it is a line, the force, if it's a line like this, then to find the area is easy. But if it is a curve like this, to find the area, you have to again use the integration. But here I must tell you what is this area. This area under the graph is simply work done. So I must say work done is area under force versus position graph. You understand that?
Yes.
Is that right?
Yes.
So whenever you have a force versus position graph, you find area under it and find the work done, no problem.
Okay.
Is that right?
Yes.
Okay, that is good. You see, one more point I must tell you. See here. Okay, why not find work done in this kind of a graph? See here. Okay. Let me do this like this, and let me go like this. This is 2 meter. This is okay 4 meter. This is okay 5 meter, and this coordinate is 10. What's the work done?
From what point?
Area under this. Area under the whole graph, right?
Okay.
But I will find area under this triangle, then under this, then under this. Okay. So it is 1 by 2 base into height is 10. That's the area of this, right?
Yes.
What is the area of this? Plus
So
2.
1/2.
2. No, not 1/2. Not 1/2 is of triangle. This
Okay,
is
yes.
rectangle. This is 4 minus 2 into 10.
2 times 10.
This is base into height, right? And what about this? Plus 1 by 2. What's
1/2
base?
times 1
Good.
times.
Answer.
Yes.
Answer. But I think that if you are asked to find the work done in graphics, then graph must be well known. They can't give you a graph like this.
No, they haven't.
Because in that case, they may assume that you know integration, which you don't.
Right.
So I expect that graph may be some like this, so that it is a circle, so that if there's something like 0, 1, 2, 2 here, that radius of the circle is 1, and you find it's a half a circle area.
Right. Yes.
They may give like this. They may give like this. They may give something which definitely the area of such things you must be knowing.
Right.
Is that right?
Yes.
Good.
Yes.
Very nice. Very nice. Okay. Now let me go a little bit ahead. Fourth concept. Now, work done in different scenarios. I want to give you some interesting thing about work done. See here. It is an object. You are applying a force F here. You are applying force F here. Why the object will go?
In the forward direction?
No, no, no. It will not go in the force direction. It will go onto the ground. It will go onto the ground. Maybe it reaches here. And it reaches S displacement, right? The angle between force and that is theta. What's work done?
So F cosine theta times displacement.
That is right. Can I write this? It is F cos theta into S.
Yes.
Can I write it's S cos theta into F?
Yes.
That is right. Can you tell me what is this F cos theta? Or what is this S cos theta? I must tell you here. Have a look. I want to put this F into components.
Okay.
What is the component of this force in this direction?
This direction,
It is theta, it is F. What is the component of, vector component of this F in this direction?
it would be F of Fx would be F cosine theta.
Good. What is component in this direction?
F sine theta.
Good. And what's the work done?
Work is F cosine theta times displacement.
Good. What is F cos theta?
F cosine theta is the work done in the x direction.
This F cosine theta is component of force parallel to S.
Yes.
So F parallel S.
Right. Yes.
Or what is S cos theta? If I put S into components, what is the component of S in the F direction?
S cosine. Oh no.
Yeah, that's right.
S.
S component of S in the F direction. That's
S
F
sine theta.
cosine theta. That's S cosine theta. See, it is S, it is F. I want what is the component of S in the F direction. That is again S cos theta here in this direction.
Yes.
Whenever theta is defined, that's a cos component. When in this direction, it will be S sine theta. S cos theta and S sine theta. Here, theta is not defined. Here, theta is defined and it is simply cos component, right? So what is S cos theta?
That's S.
S parallel to force.
F. Yes.
That component of S which is in the direction of force.
Is parallel to force. Yes.
Yes, force has this direction and S cos theta has also the same direction.
Right.
Do we learn anything from here? Yes, we do learn. We need to multiply only two things. We need to multiply. We need to multiply. What and what?
The F cosine theta and then.
Okay, displacement.
It's displacement.
And?
The force parallel to
force. We need to multiply displacement and force, which are in the same direction.
Right. Yes.
जो फोर्स और डिस्प्लेसमेंट एक ही डायरेक्शन में है उन्हीं को मल्टीप्लाई करो बस दैट्स ऑल. You understand?
Yes.
It's a very important concept which can solve most difficult problems within no time.
Right.
We have the same formula, same meaning even, right? But in a slightly different way. You see, here You have a dot product of the two vectors. But here, I mean, they're just multiplied. But what should be multiplied to what? That force and that displacement should directly be multiplied, which are in the same
direction.
Which are in the same direction. So it's very important. Not only that, by this concept, you can solve most difficult problems. Now, let me elaborate this concept further. Okay?
Yes.
Okay. See here. Let me solve some of the questions on this. I don't know your level of those questions asked. I should have something with me here so that I know things, and I'm getting the books maybe within some 3 days or 4 days.
Okay. I
Now,
will
see here. At least you should send some questions on my WhatsApp so that I can solve them for you, right?
Okay, I will send you them before tomorrow.
Okay. This is an object. Okay, let me say it is a pendulum.
Okay.
You are applying, it is a length L. You are applying force F in this direction, right?
Okay.
And the bob goes up to here. Let me suppose.
All right.
And this is theta here. Okay. Can you tell me what's the work done by the force? Work done by this force?
So the displacement times force cosine theta.
You may say,
And
okay, work done is equal to Fs cos theta, right? But what is S? What is displacement here?
it's a curve.
It's curve.
So
No, curve is never a displacement. You have to join the 2 points to find a displacement.
Oh, yes.
This is the displacement, right?
Yes.
You have to find this displacement. Then you have to find this angle, right?
Yes.
That will give you the work done.
Okay.
You see how many things you need to know. You need to know this force, you know, okay? Then you have to find this displacement, right? Then you have to find this angle. Maybe this angle is the same as this angle, that I don't know. I have to see whether this angle is the angle between force and displacement is not this, that is this.
Yes.
This is force, this is displacement. The angle between them is this, right? So that means you have to find different theta even, not this theta, different theta here. So it becomes a complicated problem. A simple thing becomes a very complicated thing.
Yes.
Now see what I will do. Have a look. See what I will do. Sorry. Here, right? This is the force, right?
Yes.
This is theta. This is L. Particle goes from here to here.
Okay.
Definitely this is the displacement.
Yes.
Can you draw a perpendicular from here to here? Yes.
And not as displacement?
This is the displacement, right?
Yes, that's the displacement.
But I will put this displacement to two components. How many components is this? One this, other this.
Right.
From here to here and from here to here. This displacement has two components. From here to here, it is the y component. From here to here, it is the x component in this direction. So if it is L, this whole is from here to here L. What is from here to here?
It's a 90-degree angle, so we can use trigonometry.
No. It is, yes, it is 90 degrees. It is L.
Right.
It is L cos theta from here to here.
Yes.
And from here to here, it is L sin theta.
Yes.
You may do it by right angle triangle method. But for me, it is simple because I put this L into pieces. This is cos piece, this is sin piece.
Yes.
You see here, I will tell you. You see what you do and what I do. Suppose this is theta. This is L. I ask you, what is this base? And what is this perpendicular? Possibly what you do in a very nice way, stepwise way, says, okay, sine theta is equal to perpendicular by hypotenuse. Perpendicular is equal to L sine theta, right? That's what you say too. Then I say, what is this base? I say cos theta is equal to base of the triangle, that is B, by hypotenuse, the L again. Then you say B is equal to L cos theta, right?
Yes.
But no, see what I do. I make this as a vector, and this is a cos component of the vector, that is L cos theta, because theta is defined by this. It is a vector. This is the direction. The L has component L cos theta in this direction. This is vertical, this is L sine theta. Simple. This is L cos theta, this is L sine theta. The same thing I do here. It is L cos, because theta is defined with this, and it's L sine.
Oh, okay.
Is that okay?
Yes.
Now, what's the work done by this force when the particle gets over here? You'll be surprised to know it is F L sine theta answer total. You may say, how I did it and how I have come to this conclusion so quickly. Multiply two things which are in the same direction, this force and this displacement are in the same direction. I just multiply them and get the answer.
Right.
Is it right?
Yes.
Now you say, no, how do I know it should be the answer? Let me get the answer by using the same formula as you have used. I can do that also, no problem. But it's better if you remember this like this. This force and this displacement, if I multiply them both, I will get the answer, because I am multiplying that force and that displacement, which are in the same direction.
Yes.
That was the concept which I developed in the last example.
Right.
Should I do it that way?
No, I like this way.
Huh?
This way is good.
This
This
way
way is very good. Yes.
Okay. If you ask me to do that way, I will do that way also, but then also I will get the same answer.
Right. Yes.
Okay. Now, should I give more example on this, or I should go ahead?
You can go ahead.
Okay. Now, let me tell you what's energy.
Okay.
You know, a particle moves, a body moves, it has a motion. It is a motion. It has energy due to its motion. Energy due to motion.
Okay.
Energy due to motion. If somebody, a cricket ball or a stone is fast and it hits somebody's head, it will cause him injury because it was having a lot of energy because of its motion.
Yes.
Right? And that energy is in the form, that's called as kinetic energy. Kinetic energy.
Okay.
Because of its motion. Kinetic is a word that you English people know very well. Kinetic means because of motion, right?
Yes.
And the formula is 1/2 mv square.
Okay.
M is mass, v is speed.
Okay.
And it can never be negative, because mass can never be negative, and v, if negative, square of it will make it always positive. So this quantity is always positive.
Yes.
If you want to prove that this kinetic energy, you see, this is the formula for kinetic energy. I can prove it in a moment. If you don't want that I should prove it, that I will keep it like that, and I will ask you to remember this equation, right?
Yes, I can.
Okay. Now there's one more point. Suppose there is a rolling body. It spins like this. At a particular point, about a particular axis, it just spins, not rolls in the forward direction. It spins just. And it spins with angular velocity omega. What is its kinetic energy? 1/2 the same.
And mv squared.
M, not m, I, omega square. I is moment of inertia. I is moment of inertia. It is done in rotational dynamics. When I give you lecture in the rotational dynamics, these things will come up, right?
Yes.
But here you can remember it for a while.
All right.
Now, if the body is just, it is rolling and moving forward, rolling, that means the point of contact has zero velocity. It rolls, rolls, rolls. The way these tires roll on the ground, the cars move, or and the trucks move on the ground, their tires roll. Their
Oh,
tires roll. Rolling and spinning is different. Spinning is like this. At the same point, it is spinning, right? But rolling is moving on the ground like this. It rolls like this. The point of contact with the ground has zero velocity with respect to ground. The point which comes into the contact with the ground has zero velocity, and the body starts rolling. And you have an experience of rolling. Rolling is smooth and nice, and spinning is rubbing with the ground. That's not good. When the tire spins, sometimes there is frictionless surface, or there is slippery road, and there's a skidding and slipping. That's not good. But rolling is better. Rolling is nicely moving tire in the forward direction. The condition for that is the point of the tire which touches the ground has zero velocity with respect to ground. Okay, that is the rolling. That is when we go to the rotational dynamics. Possibly I will discuss these things there. Anyway, now let me go to, it's a kinetic energy sort of a thing. Kinetic energy is when the body just uh, translates, not rolls. It is kinetic energy is 1 by 2 mv square.
okay.
When it spins, its kinetic energy is 1 by 2 I omega square. When it rolls on the ground, and its center of mass has velocity v, then its kinetic energy is 1 by 2 mv square plus 1 by 2 I omega square both. And this v and this omega. This v is the velocity of center of mass, and this omega is angular velocity. They have a relation in rolling. They have a relation, that is v is equal to r omega. Velocity of center of mass and omega, there's a relation between them, that is this. I think that for the time being, these relations you remember, I will take care of them when I go to the rotational dynamics in full detail, right?
All right.
We don't need them much here. Now let me go to a very important concept, work energy theorem. Work energy theorem. You see, it is very beautiful theorem. It states that work done by all the forces of the world, work done by all the forces, work done by all the forces, work done by
All the forces
on the object
on the object
is equal to, yes,
is equal to
change in kinetic energy. That's all.
um,
That means delta W, that's work done, is equal to delta K. Work done by all the forces of the world, of the universe. जितने भी फोर्स से जो काम कर रहे हैं एक ऑब्जेक्ट पर, उनका नतीजा यही निकलता है कि वो एक ऑब्जेक्ट का काइनेटिक एनर्जी चेंज करते हैं. तो ऐसे कुछ इज इक्वल टू 1 by 2 m vf square. Vf means final velocity square minus 1 by 2 m
v initial square.
v initial square. This is the rule. It is such an important term in physics. It needs respect and it needs a little more time to do it, right?
Yes.
So I will give it more time. So I will prove it. I will prove it in a moment. Maybe it will take me a minute to prove it.
Okay.
I can prove it in many ways, but I want to prove it the way is quite easy for you.
All right.
See here. Let me prove it. It is an object here. Its mass is m. Let me suppose its velocity is v1. Yeah, v initial, right? Its velocity will remain constant if there is no applied force, right?
Yes.
Its velocity will remain
Constant.
If there's no applied?
Force.
Okay. Now I apply force.
Okay.
What will happen to this object?
The velocity will change.
Good. Its velocity will change. It will accelerate over a distance here. Okay. It moves and moves and moves and moves here. It travels a distance. How much?
S.
You call it S, you call it X, you call it anything. Okay, S, you say, I should say S, okay. Now here, this force is now removed. Now what will be its velocity?
It will have V final.
Good, V2 I call that, right? That would, V final would have been much better because 2 is not 2, 1 is not 1. It is initial, it is final. But up to here, you are applying that force. So force is applied from this position to this position. And once you remove the force, what will happen to velocity?
It will decrease.
Once you remove the force, what will happen to velocity?
It becomes V final or V?
Now here the velocity is V2 or V final. But now you remove the force. This velocity will now onwards remain constant.
Okay.
That will not change because now you remove the force. But from here to here, you apply force and velocity goes on changing. And finally, the velocity is V2. But from here, you are not applying any force. And the particle or the body will continue to move with velocity, right?
Yes.
That's good. Can you tell me what is work done? Delta W or W? F?
Fs.
Good. Cos?
Cosine theta.
But theta is 0 because force and displacement are in the same direction. You see force and displacement. Fs, simply Fs, right? You can write Fs cos 0. But cos 0 is 1.
Yes.
Or multiply that force and that displacement which are in the same direction. They are in the same direction, they just multiply.
Yes.
Haven't I told you that if force and displacement are in the same, just multiply them. Multiply that force and that displacement which are in the same direction. You just multiply them.
Right. Yes.
Good. Is equal to. What is force? MA.
Yes.
Okay. Force is MA.
Yes.
Okay. If I write it 1 by 2m into AS. Is that correct as this? No.
No.
Where are 2 here?
Then it's right.
Good. If I write 1 by 2m here, and if I write it as V2 square minus V1 square, is that wrong?
No.
If I remind you, V2 square minus V1 square is equal to 2AS.
Yes.
Base formula.
Right.
You remember this formula, or should I derive it once again for you?
I remember. It's the big
Okay.
five.
It's 1 by 2 mv2 square minus 1 by 2 mv1 square. Final kinetic energy.
Yes.
Minus initial kinetic energy.
Right.
That is change in kinetic energy. So work done is change in kinetic energy.
Yes.
Easiest way of deriving a simple thing. There are many other ways, but I prefer this way because medical students in the US don't know integration. They don't know much about calculus. I want to avoid calculus as far as it is possible for me.
Okay.
Now, work done by all the forces of the universe is equal to change in kinetic energy.
Okay.
Right?
Yes.
Now, should we give some examples of work energy theory?
Okay.
Suppose there's a car, car is moving with velocity v0. Can you tell me, it applies the brakes, right? When it applies the brakes, it creates a backward force. This is called braking force, right? Braking force is nothing but it's a frictional force between the tires and the ground. You see, when you apply the brakes, tires stop they stop rotating. When they stop rotating, they rub with the ground, and when they rub with the ground, friction force is produced. So when you apply the brakes, it is basically you are creating a frictional force with the ground, and that stops the car, right? When you apply force, the will car stop there itself, or it will travel a distance before it stops?
Travel the distance.
Yes, certainly. You should move very slow so that you can stop your car within a short small distance. If you are moving faster, you will stop the car over a longer distance, and there may be an accident. That's why it is advisable to move slow. Okay, that we will prove it from here. If you are moving faster, why it is advisable to move slower or to move not at that high speed? Because you see, when you apply the brakes, you don't stop there on that point or on that spot.
Yes.
You always travel some distance, and I will prove here. If you are moving fast, you will stop over a longer distance. If you are driving slow or at less speed, you will stop over a shorter distance. You will stop over a shorter distance. Yes, and that is good because that will avoid the accident. Now here, final velocity is 0 when the car stops, right?
Yes.
Tell me over which distance this car will stop. See what I will do.
Okay.
Work done is equal to change in kinetic energy, right?
Yes.
Work done by whom?
The frictional force.
What is that?
Frictional force times S minus frictional force times S.
That's right. Why a negative?
Because it's going in the opposite direction from
That's
the
good. This
distance.
X is forward and F is backward. So angle is 180. It's minus.
Yes.
You should remember when force and displacement is opposite, the work done is negative, right?
Yes.
That you should remember forever.
Right.
But don't remember it badly so that you say that frictional force always does negative work. No.
Right.
Frictional force need not do negative work all the time. But here it does negative work because it is backwards, forward, and frictional force does negative work here. What is change in kinetic energy?
1/2 mv final squared. Oh, so that would be 0 plus minus 1/2 v initial squared. 1/2 mv initial squared.
Right?
Yes.
What is x?
We have to solve for that. So x equals mv initial squared over f. 2f.
Yes, 2 here. That's right. Good. That means if your speed is more, x will be more. You will stop for a longer distance. So you should keep your speed lower so that x is smaller. The equation tells you that. More this, more of this. Less this, less this. ठीक?
Yes.
Tomorrow I will give you one more lecture on this, and at the same time I will get questions from your side on work, power, and energy, and I will show you as many questions as possible tomorrow. Right?
All right.
Is it sufficient for today?
Yes. Perfect.
Okay, that's good. Take care.
All right. Thank you. Allah.